Hello everybody, and welcome to this series of lectures on computer architecture. Today I want to talk to you about numbers, about the existence of the numbers. Do the numbers exist? Well, what may surprise you is that numbers, they do not exist in a computer. Actually, they do not exist anywhere in the world. How can it be? Well, let me explain it to you in this way. Let me tell you the difference between physics and sciences and mathematics. That's not a science. Physics or sciences are about the real world. And in this real world, we want to understand how it works. So we form hypotheses about how it works. And then with experiments, we can test how if this hypothesis can stand up to scrutiny. So we can actually only debunk hypotheses. Something is true until proven false. While in mathematics, on the other hand, we have an imaginary world. We start with axioms, which we assume to be true, and then things are correct within that framework of the axioms. So these things we can actually prove to be 100% correct without doubt. To know if something is in the real world or maybe in the mathematical world, we can see that if it has an SI unit, the Système International d'Unité, if it has an SI unit, then it is true. Then it is real. Well, true, maybe not, but it is real. So what are the SI units? That is length, mass, time, current, quantity, temperature, and luminous intensity. And then, of course, also derived units based on these. For instance, speed, which is length per time, or meters per second. That is then also is real. So if it has an SI unit, if it doesn't have an SI unit, it's real. What about these things then, the numbers? Well, the numbers are not SI units, so numbers are not real. Numbers are only in our head. And how does this can this be true? Well, once again, you start with axioms and then build on these axioms, and then you prove things to be true. To give you an example here about mathematics, here we have what you have learned in secondary school, I hope. You have three angles of a triangle. Actually, the sum of these triangles, as you know, is 180 degrees. But that is actually only true because you started with the axiom of a flat world. And as the real world actually is spherical. Well, I hope you agree that the real world is spherical. And in this case, the sum of angles is not necessarily 180 degrees. In this case, for instance, 90 plus 90 plus 50, that is 230 degrees. So you can actually have a world that is imaginary, a flat world, and you can have a world that's imaginary, it's a spherical world, and they can have different properties. Well, of course, the mathematics can be true, it can apply to the real world, but it can also be the case that it doesn't apply to the real world. So we have to be very careful. Now, how does it then go in our computer? Well, the computer actually doesn't have numbers, it has only voltages. Or actually most computers work with voltages. For instance, here we have the TTL, transistor logic computers, and they work with 5 volts and 0 volts. So we have what is real are the physical levels, 5 volts, 0 volts, 5 volts, 5 volts. For instance, this could be 5 input lines of a gate. Of course, what we can do then, we can map it to a mathematical world. For instance, we can then map it to Boolean logic levels. We can say, just by convention, it's simply a convention, that 5 volts is true and 0 volts is false. And then again, 5 volts true, 5 volts true, and so on. So we just map it. These things, they do not exist. There doesn't exist true or false. We might have well have called it red and blue, whatever. But the voltages exist, and this is some kind of mapping we do in our head. The funny thing is that these logic gates that we have that work with these voltages, they seem to implement then our Boolean logic. So now we have the problem, we have the idea, what is actually going on? Is the mathematics actually describing the working of the computer, or is the computer actually implementing our mathematical ideas? Well, if you're the latter, then you're probably now following a course in a mathematics department. While if you're from the former, then probably you're having now a course in informatics from an electronics department. Either way can do. The thing is that the real computer works with voltages, while our analysis of the computer, how it works, can be done with mathematics. And we can actually continue this to show you that actually you can do other mappings if you want. You can also say that 5 volts is a 1 and 0 volts is a 0. These are not numbers, these are just symbols. 5 volts is a 1 symbol and 0 volts is a 0 symbol. We call this binary logic levels because actually this is nice. It has 2 possibilities and we call them 0 or 1. We can also then join them, these 4 levels, and actually then say, well, we give them a weight. This one is the least significant bit and this is the most significant bit. And then if we can convert this, we just sum it, as we see in the next lecture. This number then represent the number 11 in a decimal value, or 1011 in a binary value. Or actually, as we will see, it can also represent then B, the hexadecimal value B. So these voltages that we have here can at the same time represent Boolean logic levels, binary logic levels, decimal values, and hexadecimal values. So from everything from voltages to hexadecimal values. Anything is possible. You can map it also in another way if you want. So the message that I have for you here today is actually that everything that we are doing analysis is conventional. When we analyze the computer with binary numbers or with ASCII values or with flags or whatever, these are all conventional ideas. What really is going on in the computer is voltages or currents and charges and things like this, and the resistance states. This is real. The rest is actually only in our head and it's a convention. And in the next lectures we will see the conventions about number systems. See you in the next lecture.